I want to talk about two things that we brought up, right? We talked about how to make these things work better. We talked about making sure that your components are correct so that the equation matches reality. We're going to talk about noise briefly, and we're going to talk about calibration. When we talk about noise, what we're going to be talking about is signal processing. And we will be doing signal processing in this course. That's a fancy sounding thing, but I believe the most powerful tool in signal processing and the one that is the most universally used, as in I would imagine it's used in every biomedical instrument, is to average. This is a very, very powerful tool in signal processing, right? I'm measuring the height of a person. They're a little person, all right? And I'm measuring their height, and I have a ruler, just a 1 centimeter, 5 centimeter, 10 centimeter ruler, right? And I take a measurement, keeps going here, right? And I measure that this little person is 10.1 centimeters. Okay. But it's really important to get this right. So I go in and I measure again. And now I measure 10.0 centimeters. Oh, okay. Now it's really important to get this right, okay? So you measure again, 10.2 centimeters. Oh, okay. Going again, 10.0 centimeters. Well, that's good. That's kind of like this, right? And you're trying to figure, and then that's it. You get no more measurements, right? Tell me as well as you can, right? As reliably as you can, what is is it the first measurement you made because you go with the first? Is it the last because you go with the last? All of you have the intuition here, right? A simple thing to do would be to average these values, right? Which, as you know very well, you would do by adding them up and dividing by the number of samples, right? Now, in this case, what would we get? 10.0, 10.1. It would be 10.1? Yeah, no. What would it be? 10.075. 10.075 centimeters. I actually like that it came out that way. Notice that this has more precision than anything that we had reported before. But that's how the average came out. If I only wanted you to report it to 1 decimal point of precision, then you would round this to 10.1, and you'd say my best guess is 10.1. Averaging is very powerful, right? It's very powerful, but it's very limited, and let me show you why. I'm going to add an issue here. The ruler that you were using had this little knob on the bottom. And this knob was 1 centimeter high. And the increment started from here. What I'm trying to explain is, right, that because of this, there was a constant 1 centimeter error. Right? The ruler didn't start at their feet, right? At least the measurements on the ruler didn't. It started 1 centimeter up. So even if their height was exactly 10 centimeters, because the ruler started 1 centimeter off the ground, you would have measured 9 centimeters, right? Or in this case, if their height was 11 centimeters, the ruler had an error in it, right? So the error here that it added, let's write error, was 1 centimeter. 1 centimeter, 1 centimeter, 1 centimeter. Their height was 9 centimeters, right? You could take all the measurements you wanted until, they say, the cows came home. You would not remove this error, right? One thing you notice about this error is, let's average the error. What is the average of this error? 1 centimeter, okay? So what I'm trying to illustrate to you here is that averaging is very powerful, but averaging relies on something in particular, that the averages of the errors are 0. So if, for example, this is not 1 ohm, but 1.1 ohm, all right, averaging will not fix the problem because you're going to hit the same bias again and again and again. You're going to get the same calculation error, Is it turns out that there are many sources of noise where they will average out. So we'll go back to a different situation here. This was not the case. And the error in this case was, let's say it was 0. In this case, it was minus 0.1 centimeters plus 0.2 centimeters, 0 centimeters, right? In this situation, the error is closer, right, to averaging out to be 0. So use averaging, all right, but beware of it. Now, how many averages should you take? Should you have stopped here? Should you have kept going? This is going to be a very practical issue for you, right, as you move ahead. There are many mathematical descriptions of this, but I'm going to give you a very good rule of thumb. If taking more measurements doesn't change the calculated average, then you've probably done enough, right? If you went here and the average was, something, and then you took another measurement and the average changed, oh, maybe we should take a few more. So that's one rule of thumb. They should probably take as many samples as are needed. All right.